Welcome to this month's STEMS webinar. So today we are very happy to welcome Ben Nachman as our speaker. So Ben is a staff scientist at the physics division at the Lawrence Berkeley National Laboratory. He's there a group leader of the machine learning for fundamental physics group. And as you might have guessed, his background is in physics. He's trained in physics. He has a PhD from physics, a PhD in physics from Stanford. But also he has a lot of interest in statistics and machine learning. In fact, I learned that he has a PhD minor in statistics. So already, it goes way back to his PhD times that he has had an interest in kind of statistics and machine learning. And after he got his PhD, he moved to Berkeley lab. He was first there as a Chamberlain Fellow, and I believe he has been there since then. So his research is on machine learning for data analysis, especially in particle physics, and he has done very fundamental and important work there, for example, on things like decorrelation algorithms, anomaly detection algorithms, likelihood-free inference, and related things. So really sort of taking a leadership role on kind of machine learning for data analysis in particle physics and sort of addressing this kind of unique challenges that arise with particle physics data using modern machine learning techniques. So he's a member of the Atlas collaboration at CERN, and some of his work has then been applied for data analysis at Atlas. And yeah, with that, we will move on to his talk. So his title is Building Robust AI/ML Methods for High-Energy Physics. So Ben, please go ahead.
Yeah, thank you very much for the opportunity and for the kind introduction. It's a pleasure to be here virtually. All right, so yeah, first, I need to explain to you what is high-energy physics. Probably many of you are familiar, but I'll say a few things, and then I will pivot into how we can apply machine learning in a robust way. All right, so first, what is high-energy physics? So maybe I'll motivate what is high-energy physics by the questions that we're asking. So we're trying to explore the fundamental structure, the smallest distance scales, and how the other scales from them emerge. And there are deep theoretical and experimental questions that motivate this exploration. So on the theory side, one is about the Higgs boson. So perhaps you've heard of the Higgs boson. It was the last fundamental particle to be discovered. Well, it's fundamental as far as we can tell. It was discovered almost exactly 10 years ago. This is the 10th anniversary of the discovery in July. In the US, July 4th is a holiday because of Independence Day. And in Europe, July 4th is a holiday because it was the discovery of the Higgs boson. But in answering many questions, it also raised many more. So for instance, why is the Higgs boson mass what it is? We don't really understand why, and it's sort of a problem. It's a little bit too light and a little bit too heavy. So that's a problem. And there are other problems as well. So another one I'll stress is this one about what's called the strong CP problem. So if you just Google online, like, what does a neutron look like? Neutrons and protons, they make up almost everything. They're made of quarks. There are up quarks and down quarks. Neutron is 2 down quarks and 1 up quark. And probably you see pictures like this on the internet, nice little triangle. There's like 3 blobs, and the blobs are kind of oriented in a triangle. But actually, in reality, the neutron looks more like this. The quarks happen to be in a line. They have almost no dipole moment, and we have no idea why. And so this is reality, and it's kind of motivated a lot of interesting studies. So those are kind of theory questions, but they're also experimental questions, like things we've discovered that are just by observing the world, and they've puzzled us. So one is the existence of dark matter, and there are many ways that we've observed dark matter astrophysically. One is this beautiful picture that shows the bullet cluster, or one of them is the bullet cluster interacting with another cluster of galaxies. And what you see here, the orange bits are the visible matter, things we can see like galaxies, and then the purple bits are what we infer from the gravitational potential. And so what we see is that basically there's this big gravitational bits that are going right through each other, and then the visible parts are interacting more strongly. So it seems like there's a lot of gravitational mass that is not in the visible matter, and this is an inference of dark matter, stuff that looks like interacts gravitationally, but not with our visible matter. And we don't know what dark matter is made of. We know it exists. We have never been able to produce it in the lab or observe it using any of our experiments, except for astrophysical ones. Another question is like neutrinos. We know they exist, but they have a mass, it turns out. And we don't know where the mass comes from or what it means. And this is sort of another interesting puzzle that has motivated a number of explorations. Okay, so those are some deep questions that kind of give you the sense of like why we're doing what we're doing. But now let me sort of pivot a little bit to how we try to answer some of these questions. And in particular, what is the workflow for data analysis in high-energy physics? Ultimately, we'd like to learn something about what is the theory of everything. Theory of everything here is a high-energy physicist's way of saying we want to know what is the fundamental structure, what are the rules that govern, what are the basic particles, and how they interact with each other. And we want to do that by making observations on nature. And so this is sort of the inference path. If you like, the left-hand side is theory and the right-hand side is experiment. I didn't write those words because I think sometimes putting those different camps can actually be more hurtful than helpful. But anyways, on the left-hand side, we have our theory, we posit it, and we have simulations that we can run to produce data that look like real data. They have the same complexity. We have to run the same reconstruction algorithms in order to do dimensionality reduction. And then on the right-hand side is kind of the same path, but it's the real thing. So we have nature, we build giant experiments to be able to observe various properties that we can predict. And then there's this comparison between left and right to be able to do inference. Okay, now this is sort of the classical setup, but machine learning, and in particular modern machine learning, are revolutionizing basically every aspect of this chain, both on the theory side and on the experimental side, and how we compare theory and experiment. So on the left-hand side, both in the forward direction, so accelerating or otherwise improving the forward models is being accelerated with machine learning, then the inference, which is kind of going backwards this way. So parameter estimation, deconvolution, those are all being improved with machine learning. On the right-hand side, there are some more basic low-level improvements, so experimental design, operations, quality assurance, as well as sort of the more downstream tasks like reconstruction, or maybe what other people would call in general data curation. And then the actual inference tasks, so like the middle part here is sort of the comparison of theory and simulation, is also possible to improve with machine learning. And more or less, machine learning allows us to do things we were unable to do before, because we can optimally combine simulations with data, we can explore large parameter spaces, and we can explore large feature spaces holistically, which is something that has been hard for us to do, basically impossible for us to do in a complete way before. Now, this is a really exciting topic with a lot of literature. In fact, many people in this call have contributed to this exciting area. I'm not going to talk about most of it at all. I could give a seminar basically about any one of these things, but instead I'm going to focus on one particular topic, which is this topic of robustness. And even in the area of robustness, I'm only going to focus on one particular sub area of that topic because I think it's pretty interesting and has some nice statistical implications. So let me get into that. And so for that, I'm going to use as an example, which is sort of a common example, thinking about a search for new particles. And I want to build sort of simplified search for new particles in order to explain where this robustness question comes in. So let's say I want to search for new particles. This picture here is an event display from what a collision might look like in the ATLAS experiment. It's a proton-proton collider, so protons are coming in from the left and from the right. Those are these gray arrows. And then out goes a bunch of collision debris. So there's these orange charged particles, and then there's like green and yellow blobs, which are deposits in our calorimeters. And from this, we try to reconstruct what was the particle physics, the fundamental interaction that happened at the center, this giant question mark. And we want to discover new particles with a large mass. And so in order to get a large mass, we need to pump in a large energy, E equals mc squared. And so large energy equals large mass. So the Large Hadron Collider, as its name suggests, is the largest terrestrial experiment with the highest energy to be able to probe the most massive particles that we can possibly imagine creating synthetically in the laboratory. Okay, so let me think about how an analysis would go. This is sort of a simplified version, but it actually has a lot of the salient features of a full-blown particle physics analysis. So the idea might be something like the following. I'm going to look for a new massive particle. And so what I'm going to do is I'm going to reconstruct the mass of the event from all the stuff I can observe. And the mass, which is a one-dimensional feature, will be like the x-axis of this plot that I'm showing right here. It says physics-informed feature, which is often a mass-like variable, but sometimes it's a little bit different. And this is going to be like a histogram. So the y-axis will be like counts in a given bin of the mass. And so if there's some new stuff, the signal will be localized somewhere. And in particular, be localized at the mass of the particle. We don't know ahead of time where it is, so it'll be anywhere on this range, but it'll be localized somewhere. And then there'll be a lot of other stuff that's produced. So the standard model, which is most of our understanding of the existing particle physics, is very generous, if you like, and produces lots of stuff that can look like a signal. But the main feature of the standard model is that it doesn't have a resonance. It's not peaked somewhere. It sort of has a continuum background in many of the dimensions you could look at. And so the orange here is the known stuff, and the green thing is what we're trying to look for. Okay, and the main point of this is that the orange is smooth, the green is peaked, and the green is way rarer than the orange. If the signal were very common, we would have found it already. Okay, and so what we might see in data is the black. So we don't get to know orange and green. That's just me putting on labels. But of course, all we get to observe is the black. And the question is the black more consistent with the orange or the orange plus green? That's like the basic analysis we might want to do. And there are a lot of variations on the theme and many analyses that try not to use simulations or predictions in this way. That's a whole area of anomaly detection, which I'm not going to talk about at all today. So this is the kind of analysis I'm talking about. And so we get to observe the data like this. And the question is, how can we estimate the significance of that bump? Is there a bump, and how significant is it? And so often our simulations are not good enough, so I can't just make this orange curve. And so we need, our simulations are excellent, but not always good enough. And so in cases like this, often what we do is we do some kind of parametric estimate. For instance, we learn directly from the data by making a signal region around where a punitive signal might be, and then a sideband region away from where the signal might be. And I said we don't know where the signal is, we're going to eventually scan the dark gray region. And so we can do some kind of fit. The functional form of the fit might be informed by what we understand about high energy physics and scattering processes, but it's going to be an approximation. And so we're going to fit that directly to data because we don't know the parameters a priori. And so we can exclude the dark gray region, then we can do a parametric fit using the sideband region and interpolate the function into the signal region. And then what we can ask is how consistent is the data, the black dashed, with the prediction. So that's going to be our p-value. And if that p-value is order 1, then we say there's no evidence for something new. And if the p-value is very small, then we start thinking about booking our tickets to Stockholm. And we get really excited. Okay, so that's like more or less how this will go. And then we can start thinking about, well, where does machine learning come into play? This seems like a pretty simple procedure. So now I'm going to generalize this a little bit. So we have this one feature. Now I'm going to call it feature 1, not mass, where feature 1 is a special feature where we know the signal, if it exists, is localized. And then there's going to be a bunch of other features. In this case, there's a feature is up to n, where n could be large. Could be a few tens, hundreds, thousands. The full detector in all of its glory has something like 100 million readout channels. So in principle, it could be quite high dimensional. So we're going to use other dimensions to try to enhance the presence of the signal if it exists. So one way we do this is through this fully supervised, which is most analyses at the LHC. So we have, let's say, simulations of the signal in the background. They may not be good enough in the background case to get exactly this curve, but they'll be good enough to develop a classifier. So we can train a classifier to distinguish signal from background, fully supervised, using all these n-2 features. And the classifier score distribution as a histogram will look something like this. It will separate to put the signal on the right and the background on the left, and then we'll make a cut somewhere and say keep only events to the right of that threshold, and that will remove most of the background. So the orange goes down, and ideally it will keep most of the signal. So the significance of the bump, if it exists, will be amplified. So that's the goal of this machine learning approach. And ideally, it would look like this. So we make a cut, lowers the background, keeps the signal, and so the signal over background, signal to noise ratio goes up. That would be great. So it looks something like this. In the ideal case, you can see the bump now looks more pronounced above the background. Okay. So what happens in practice? In practice, what can happen is this. So even though we don't use feature 1 in the training of the classifier, all of our features are correlated. And so the neural network, if it's smart, can infer feature 1 from the other n-2 features. And so because the signal is peaked at a certain place, it will try to sculpt the back. It will try to focus in on that region of the parameter space. And so when you make a cut on the classifier, it will look like this. And the thing is, this is just the background. There's no signal here. So it makes the background only case look like signal. And this is a problem because it's very hard to fit this function. It's hard to fit a peak on top of a peak. Fitting a peak on top of a smoothly falling background is easy, but fitting a peak on top of a peak is very hard because it requires understanding very carefully what the peak structure looks like for the background. As I said, we often don't know that. We might know roughly what family of functions the background will roughly follow, but this will induce a strong correlation between that fitted function and the actual parameters of the signal. Okay. So yeah, just to review, this is the problem. The problem is that we want to train a fully supervised classifier to distinguish signal from background. We make a threshold and throw away most of the events. And most of the events we throw away will be background. And ideally, we would preserve the signal. So at a relatively high true positive rate and a very low false positive rate, that's what we care about. The ideal case would be that the background shape is still smoothly falling. And in reality, what happens is that the neural network can infer this feature one from the other features, and it basically sculpts a bump, which is a problem. Okay. So how do we get around this? Now, one solution is that we can make the classifier independent of feature one. So imagine I had a classifier that was independent of feature one, then if I make a threshold, the shape will look exactly the same. So not only will it still be smoothly falling, it will be exactly the same as smoothly falling background. It's just the counts will go lower. And there's an asterisk here because this is certainly sufficient to solve the problem, but it's unnecessary in the sense that imagine instead of being independent, I had the classifier be a linear function of feature one. It's not hard to see that if it was a linear function of feature one, you also can't sculpt a bump. Sculpting a bump requires having at least a polynomial dependence where you can have a local, basically the derivative here is 0. So you have to be able to sculpt the bump, which requires at least a quadratic dependence. And so there's a larger category of options where you don't sculpt the bump, but it's not independent. And I'm not going to talk about that here, although we will mention one method that briefly that does have that property. So I'm going to focus here on independence. And in high-energy physics, we call independence decorrelation. It's a stupid name because they're of course correlation and independence are not the same thing, but I'm stuck with it. So we call it decorrelation. So this is the problem of decorrelating a classifier from, in this case, feature one, or we typically call it the resonant feature or the mass. Okay. So how do we do this in practice? So let's say we want to train a neural network. So training a neural network means minimizing some loss functional. So here's a loss functional. We have f is a neural network. And I want to minimize this loss functional, and usually it looks like this. You have some term for the signal and some term for the background. So 1 means signal. Remember, this is fully supervised, and 0 means background. This is the usual case. L classifier here is the classifier loss function, which could be like the binary cross entropy or log loss, or it could be like the mean squared error, whatever your favorite typical binary classifier would be. So if you do this, X here will be all the features that you want to learn, and it could infer M. As I said, M and X are correlated, so if you just give it X, it can learn M, which is not what we want. So instead, we can customize the loss function by adding an additional term with some hyperparameter lambda that will tell us how much we care about decorrelation. And there's this L decor here, which is the decorrelation loss function, which tries to make F and M independent. And so here you see this last term, there's no signal or background. In fact, usually you just give, it's just over the background, because we don't want to decorrelate from the signal, because the signal, they are correlated. But in the background, we want the M and the F of X to be independent. And yeah, I put correlated in quotes here, because like I said, we call this decorrelation, but we want it to be independent. And now what I'm going to do is spend a few minutes talking about different choices for L decor. Okay. So there are a number of proposals. Let me just give you 3. One is to use an adversary. So an adversary is a second neural network that tries to learn, there are many ways of doing it, but one way of doing it is to try to learn M from F. So if it can't learn M from F, then there's no information about F. There's no information about M in F, and they're independent. And another possibility is to basically make L decor the actual correlation. Imagine this was just the correlation coefficient between F and M. If it were if that were small, then they would be uncorrelated. And in general, you can generalize correlation to be a different related metric. And one that's been well studied is the distance correlation. And the distance correlation is like the linear correlation. So probably you're familiar with the Pearson correlation. That's the left pictures here, where as you might expect, if you're totally linear, then it's a correlation of 1. And as you become more blob-like, the correlation goes to 0. But the problem with the regular correlation, as you all are super familiar, I'm sure, is that there are many configurations where the correlation is exactly 0, but there's clearly a strong dependence. So the distance correlation is a generalization of the correlation, and it has the nice property that it's 0 if and only if the 2 features are independent. But otherwise, it has some similar properties with the regular correlation. Okay, and the last is this other technique called mode decorrelation. And what this does is basically it tries to explicitly penalize the CDF in bins of mass from being different across different values of the mass. And so it sort of explicitly controls the dependence of the function, well, in this case, the CDF, on that using bins. Okay, so let me go through each of these one at a time to give some pros and cons. So for adversaries, it's a super flexible approach. It was one of the first ones that was explored. It requires, like I said, the second neural network. So the benefit is that it's very flexible, and M can easily be multidimensional because it's a neural network. So you can feed in as many features as you like. The disadvantage of using an adversary is that in general, it's hard to train. It requires a whole other neural network. So that requires, like, if you have n parameters in the original neural network, you'll have something like 2n parameters if you have an adversary of the same size. Although typically the adversary is a smaller neural network. And it's a mini-max problem because the classifier is trying to distinguish signal from background, and the adversary is trying to predict the mass from the classifier. And they have sort of different objectives. And so this can be a challenging configuration to try to optimize. The distance correlation is nice because there are no free parameters. You just have the hyperparameter, but it's just the correlation or the distance correlation. So there's just a function you compute. And it's convex. You want to just strictly minimize it. So it's easier to train in that way. The disadvantage of the distance correlation is that it can be memory intensive to compute the distance correlation accurately. So if you imagine if you have a bunch of samples and you want to compute the correlation, you look at all the pairs. And so that requires large batch size and therefore a memory if you're training on a GPU, which is not small. So that can be a challenge. Then there's this mode decorrelation. As I mentioned, this sort of forces the CDF to be the same in all bins of mass. So the one advantage of this is that it readily generalizes beyond independence. This is the only method I know of that has this property. So you can easily require that the CDF be either independent of the mass or have a linear dependence on the mass, or say a quadratic but monotonic dependence on the mass. There's also no free parameters and has a small memory footprint. So unlike Disco, it's easier in that way. The disadvantage is that in its simplest form, the way we pitched it so far is that it requires binning in M. So it has some discrete features. I don't think this is fundamental to the setup, but it's the one that's been studied so far. And certainly this is something that we'd like to generalize in the future. Okay, so now let me show how these work in practice. Let me start with the left-hand picture here. This is so this is going to be a case of one particular example of looking of some new particle. In this case, it's not a new particle; it's a known particle for calibration. So there's going to be, on the left-hand side is a histogram. The x-axis is the mass of some jet of hadrons. Hadrons are like protons and neutrons. They're the particles that we observe in our detectors. And the mass of this jet will correspond to the mass of the particle, if there's a particle. Otherwise, it's just some random combination of hadrons, which will have some continuous background, some continuum smooth shape. So the red is the background standard model, and the black is a highly energetic W boson. And the W boson mass is about 80 in the units of the x-axis. And so you can see the black has a peak around 80. So that's the signal in the background. And we'd like to train a classifier to be able to enhance the presence of these W bosons. Okay, so the left-hand side is signal and background. The right-hand side is background only. There's no signal on the right side. So let's start with just the black line. The black line is we train a classifier to distinguish signal from background, make a threshold, and we see what we see. And we're not using the mass explicitly in the classifier. We're using a bunch of other features, properties of the jets. And unsurprisingly, the mass can be inferred from those features. And so when you make a cut, then the background looks just like the signal, and in fact, it's peaked at 80. So you can see nicely that the peak, well, horribly, that the peak is at 80. So this is not good. Basically, the neural network is smart. It's learned to infer the mass from the other features, and it just picks out that mass. And this will be very hard to fit because it's a peak on top of a peak, and that's not what we want. Then there are a bunch of colored lines, everything else, and they all have some decorrelation. So I want to focus first on the adversary, disco, and mode 0. So the blue, orange, and green. And if you can't distinguish the colors, it doesn't really matter. It's these ones that are all kind of clustered together, these three that you can see here. Hopefully you can see my mouse. And they all are enforcing this independence, and they basically achieve the same performance. So you can see that these curves all look like the red one on the left-hand side. So the background shape looks basically unchanged after applying this threshold. That's because they've been constructed so that the classifier is independent of the mass. So when you make a threshold, the shape looks the same. And we have far fewer events, but the shape is the same. And fitting these spectra to a smooth function would be no problem. and they roughly have similar performance. Although I said there's like different pros and cons in how you train them. They're not all easy to train and have different requirements. Then I'll show. Then there's two other lines here. There's purple and the brown ones, and these ones are this mode decorrelation where we allow for some dependence on the mass. So this top one allows for linear dependence, and the purple one allows for quadratic but monotonic dependence. If you allowed for unconstrained quadratic, you would be able to scope a bump, but when you can easily require that the quadratic function is monotonic, and then once again they're both smoothly falling. And the point is that by allowing for some dependence, you actually can improve performance because you can have more sensitivity by allowing for it to depend on the mass, but you still don't scope any bumps, which is what you want. Okay, so that's the challenge, and that's the partial solution. You can see here. Now what I want to say, make a statement about how this decorrelation connects more generally. So this is a partial solution to this problem in high energy physics to be able to allow us to have this robust method, robust in the sense that we can then actually do our analysis, fit the background. But there are actually strong connections between this and other areas of science, society, industry, as the slide says. And this is because this is basically exactly the same problem as fairness. Right, so let's say you want to train a classifier to screen a bunch of CVs, and you don't want it to indirectly learn things like the age of the candidate or any other protected quantities. So in this case, we have exactly the same setup where we want to train a classifier to distinguish signal from background, good candidates from bad candidates, and the protected feature for us is the mass. It's a bit different than these protected features because in fairness, a lot of the features tend to be discrete, whereas for us, the feature is continuous. But it's kind of similar, and this sort of asks the question, how can we connect are there connections between the tools that we've developed and the tools that other people have developed? And it would be fascinating to explore these connections, and in particular, thinking about cases where monotonicity is sufficient or is fine. So where independence is more than enough, basically. Okay, so that was the first part of my talk. I wanted to talk about decorrelation. And in the second part of my talk, I'm going to discuss another aspect of robustness, which is prior dependence. And so the idea of prior dependence is that we often train using some simulations. I just mentioned training like signal versus background. And the training data sets are a bit different than the testing data sets. And this can induce some problems. And I want to highlight one of those problems and how we can, and at least one class of solutions. So everything I've talked about so far focused on classification. And in this second part of my talk, I'm going to focus on regression. And the regression task I'm going to focus on is what experimentalists would call calibration. So I want to learn a map from measured quantities to true values. And so, for example, let's say a particle will be given energy, hits our detector, and registers some measurements in a number of sensors. I want to use the array of measurements from those sensors to predict the true energy. That would be like a calibration task. So a good calibration, it will have the property that it's universal in the sense that it should be unbiased, even if the true values in the training data set follow a different spectrum than the test set. So what do I mean by that? Imagine I'm going to calibrate like a scale, and I have a bunch of kilogram weights, 1 kilogram, half a kilogram, blah, 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 and I want to check the scale. But let's suppose I'm going to use the scale in a case where I don't have like a uniform distribution or discrete blobs of masses. I'm going to have a spectrum, some spectrum of masses from people getting on the scale. I want it to still be unbiased. And here, that's the problem I want to talk about here. Okay, so it's not that I don't have like a domain adaptation problem. It's not that my simulation is biased or whatever. I want that the spectrum I use for training is the same as the one I want that the spectrum I use for training to not affect the performance when I test. Okay, so yeah, just another example here. Typically, we do calibrations where we'll have some simulations of our detector, and we tend to have like a uniform particle energy used during training, but in practice, the spectrum of energy is not uniform. Typically, it's like exponential or some other power law or steeply falling polynomial. Okay. So your first instinct might be, well, if I have a simulation in my detector, why don't I just train a classifier calibration? Why don't I just train a regression function to go from my sensor measurements to my true energy? Just invert the simulation that way. And that is what a lot of people do. And that would be a good idea, maybe. but now let me try to explore why that might be undesirable and why in many cases we don't do that. So yeah, my claim is that that would be prior dependent. So let's see how that works. So here's a slide with a bit more symbols. So suppose I have some features X, that's what I measure, these measurements of the sensors in my detector. I want to predict the true energy Y. So I'm going from X to Y. So one thing, and let's say I have a simulation of how, I know the probability of Y given X. That's my simulation. I can sample from that. It's my simulation. So one way of doing this would be to train a regression function, F, which would be a neural network, to let's say, minimize this loss functional that you see here. It's the mean squared error. So I want to learn a function that goes from X to Y. And if you do this, probably most of you know that the mean squared error gives you the average value. So it predicts the average value of Y given X. And you could use different loss functions and you get different statistics. So, if you use the mean absolute error, you'd get the median and et cetera, et cetera. But the mean squared error is very common and it gives you the average. Okay, so why might this be a problem? The average value of the true given the measured, Y given X. And to see that, let's compute the bias. So the first line here is just what the definition of the mean, nothing special. You can see I'm just, probability of integral of Y, P of Y. And the second line is the bias. So I want to compute what's the average value of the reconstructed quantity given the true quantity. And if this method is unbiased, the expectation value of f of x given y should be y. That would mean that, like, on average, for a given true value, I return the true value. And here is just the equation. I'm just plugging in the different quantities. Basically, it's like the expected value twice. And if you just look at this equation, you can see that this does not equal y, even if p train and p test are the same. So that's a problem. And this is where I'm talking about the dependence on the training set. So the closure we want to be true in my test set, and the f function is trained in my training set. So it depends. This p here is p train, and when I compute the expectation value here, it's over p test. And actually, even if they're the same, you don't get closure. But certainly, if they're not the same, you don't get closure in general. So that's a problem. Okay. So let's now see this with some numerical examples. How does this work? So let's say I have the simplest possible detector. It's just a Gaussian. So my true distribution is a Gaussian, and my detector is also a Gaussian. So I have some distribution where the true distribution of energies has mean mu, standard deviation sigma, and my detector smears everything by epsilon. So my detector smearing has mean 0. It's just additive noise. And let's just say these are the values. And so the y-axis is the true values, and the x-axis is the measured values. And if there was no epsilon, then it would just be 1-to-1. And because there's no added bias for my my detector, you can see it goes to 0, 0. Otherwise, you can see what it looks like. And let's say I did the MSE procedure. So here I know the function is linear, so I don't need to train a neural network. I can just do these squares. And if I fit the true given the measured, I'll get a line like the blue dashed line. And now suppose in bins of true, I compute what's the average measured given true. And if you do that, this is not exactly that, but it's something very similar. The blue is not 1-to-1, and that's a problem. So this is the average value, the predicted true value. This is in bins of measured, but you can trust me that if you make it in bins of true, it also doesn't look 1-to-1. That's the problem. And an alternative approach here is actually shown in red. The red here, it's this thing that says Gaussian ansatz. And what that is it's a maximum likelihood estimator. So the maximum likelihood estimator, so if you pick instead your predicted true value is the one that maximizes p of x given y, then that will be independent of p of y by construction. And so that will have this property that it has the desired property. And this thing that's called Gaussian ansatz, this is just one way of doing it with a neural network that doesn't require density estimation. So typically, if you wanted to do maximum likelihood, you have to know the likelihood. And in general, we don't know that. I said we can just draw samples. We don't actually know the likelihood. So you have to estimate it somehow. You could do that by doing explicit density estimation, but we showed in this paper how you can do it approximately using this thing called Gaussian ansatz. Okay, so now let me show you how this works with the particle physics example. This is the same picture I showed before. Say, you're looking for new massive particles, And this picture should look somewhat familiar. So the x-axis here is once again some mass, and the y-axis is something like a histogram, normalized. And so the background will be some smoothly falling function, and the signal, if it exists, will be some peak. And now the thing is that I've normalized them. They've been normalized here. We normalized them so that the signal is now not small compared to the background, but in reality it would be small. And so what we want to do is we want to be able to have the scale here be calibrated. And so these are just what the distributions look like. And you can see here the field histograms are the true values, and then the markers are the measured values. And there are two different detector simulations here. That's why there's this thing that says Delphs and Geant. These are just different detector simulations. So we'll just pick one of them for now. And the goal is that we want to be able to correct on average so that, for instance, the peaks are in the right place. Okay, so these are some super busy plots, but let me first focus on the left-hand side. So here the x-axis is a histogram of the reconstructed mass over the true mass. And what we want is that this ideally should be peaked at 1. And so there's blue and red histograms here. The blue is the background and the red is the signal. The calibrations are always run on the background, but we're going to apply it also to the signal. And so out of the box, you can see that the filled histograms have a peak that's much lower than 1. It's like 0.95. And that sort of just corresponds to this peak being to the left of the true value. Okay, so peak is low. But then let's say we run a calibration procedure where we do mean squared error regression. That's this MSE calibrated. And for the sample the mean is in fact 1, or close to 1. And so that's good. The blue is the one it was calibrated on. But now if I look at the red we're applying the calibration derived on the blue and applying it to the red. And you can see that not only does it not peak at 1, it's actually like further from the right answer than it was to start with. And because here the prior is just the spectrum is totally different, right? So for the background, it's this steeply falling, and for the signal, it's peaked somewhere, and they have totally different spectra, and as a result, the closure is the bias is totally different. In contrast, on the right-hand side, the filled histograms are the same. This is like just before any calibration. And then the open histograms, these correspond to this GA stands for Gaussian ansatz. So this is our approximate maximum likelihood estimator approach. And as advertised, it is independent of the spectrum that you're training or testing on. And so they both look the same and they're both peaked at 1, which is what we want. And so that shows that with a tweak of the approach using a method that is more robust, and the robustness in this sense is the universality of the classifier, that we can achieve the desired properties here. Okay, and so let me also wrap up this part by talking about how this is connected to other areas. So what does prior independence have to do with other areas of science, society, industry? And just as a reminder, so prior here, I'm not meaning in the Bayesian sense of prior, just the spectrum used for training and how it's different than the one using for testing. And this is also related to the idea of fairness. So you expect the scale at your doctor's office to be correct for you on average, even if the spread of weights was different than the calibration sample. So presumably the calibration for the scale, and there's some spring or something inside the scale, the doctor's office, and it was calibrated. The Hooke's law coefficient was calibrated by putting on some weights. And you'd like that to make sure that the spectrum of weights that were used to derive the calibration doesn't affect the weight you see at the doctor's office. And there, it's kind of a trivial calibration because the effective resolution, if you like, the epsilon of your scale at your doctor's office is tiny, basically negligible. There's almost no spread. And in that limit, it doesn't matter what you do. It's always prior independent. But in our context, the resolution, this epsilon, the effective epsilon is not small, which you can see clearly here. So, the width of the markers here, like, spread, is way bigger than the width of the histogram, the field histogram. So that means the resolution is huge, and so these effects are not small. And the bigger that width is, the more this prior independence effect matters. And I could imagine that there are many cases where this could apply outside of high energy physics and nuclear physics. It would be fascinating to think about where approaches like this would be relevant. Okay, so that basically brings me to the end. Today I started off by talking about how machine learning has the great potential to improve basically all areas of high energy physics, both on the theory, the experiment, and the connections between the two. Today, I only had time to focus on one small part of that puzzle, but an important part, which is that in order to make the best use of these tools, we need to ensure that they're robust. And a statement here is that tool is only as good as its calibration. So today I talked about two things. One is about something related to fairness. So the idea that many times we want to develop classifiers that are independent of a certain feature, a protected feature, in order to be able to fit background spectra to smoothly following distributions. And the second part of my talk, I discussed another aspect of robustness, which is regression models, where we want to develop a calibration, predict true values from measured values. And we want that when we apply that to some data set, that it's unbiased, even if the spectrum used for training is different than the spectrum used for testing. We can build robustness into classifier training and tools developed for high energy physics that may be useful in other contexts, and it'll be fun to explore how these tools can be used across not just in high energy physics and nuclear physics, but in maybe other areas of science, society, industry. And that's it. Thank you.
Cool. Thank you so much, Ben.